create a knowledge pool that can address relevant problems under the ambit of human cognition both for India and the world at large. It helps students acquire a strong background in theoretical frameworks and empirical approaches of one or more areas of cognitive science. Cognitive science is an emerging new field of study that endeavors to study the mind from multiple perspectives and disciplines by combining ideas, principles, and methods from psychology, linguistics, philosophy, computer science, and neuroscience. This knowledge is applied for developing a better understanding of how our minds, brains work while creating better products, tools, services, and policies. CoboTalks, leading the way in the human-robot collaboration space. IHFC.
Thank you, Sharvanu. So again, a warm welcome to everyone who has just joined in. So this is our inaugural talk of the first industrial seminar series, CoboTalks. Many of you who were already attending the CoboTalks seminar know that we are organizing this on every second Wednesday of a month with academic experts who are working in the area of robotics. So our new seminar series CoboTalks will be conducted on every third Wednesday of a month, featuring talks from industry experts working in the area of cobotics. Introducing our today's guest speaker, Mr. Sarthak Upadhyay, who did his BTech in Electronics and Communication Engineering and MS in Computer Science Engineering from IIIT Hyderabad, and then joined Adverb Technologies in 2019, and currently is Senior Manager in the area of mobile robotics at Adverb Technologies. So before we begin our talk, let's hear briefly from the Director of IHFC, Professor S.K. Saha. Professor Saha, over to you.
Yeah, okay. So good evening all, and I'm very pleased to see the first industry Cobo talk is starting today, and we are thankful to Adverb for patronizing some of their activities with us, IHFC, and one of them is that our tele ultrasound which we have developed together with AIMS and Adverb. And this is a concept evolved during our last visit at Adverb that Mr. Sangeet Kumar has been talking that okay, how industry can expose their problem to the world in general, so that people are aware of it. And Adverb being one of the very sophisticated company made good news in the very recent times. I'm happy that they have come forward to take this lead, and IHFC is happy also to provide this forum. So the three consecutive third Wednesdays will be offered to them, starting with today, so October, November, December. So please enjoy the problems which they have been handling it, and I'm sure for our audience, many of them will be eager to solve those and also participate in the activity, through IHFC and Adverb. Thank you, and over to you.
Thank you, Professor Saha. So now let's move to the talk and over to Sarthak.
Yeah, thank you everyone, and a very good evening. Let me just share my screen. Right. So is my screen visible?
Yes, it is visible.
Yes.
Right.
Yeah.
So good evening. I'm Sarthak Upadhyay. I'm a member of mobile robotics team. I've been working with the bin picking team. So my focus has been on perception, systems, user experience, and human robot interaction. So bin picking is a problem which is basically it's a union of computer vision and robotics. So let me just start with the first slide itself. So the agenda would be, I'll be talking about what is the 3D bin picking problem, how we have approached this problem and how we try to solve it. I'll talk briefly about software design because that is a very important component of any system. So I strongly believe system, if not 60-40, is almost 60-40 combination of system and algorithm. So these algorithms have to be wrapped around good software design so that they can scale up very well. And talking about way forward, where we want to head, what are the challenges, and how academia can basically help us in solving these challenges. So what is 3D bin picking? So as I talked about it, it's a combination of computer vision and robotics. The goal is for the robot to understand the objects in front of them, in front of it, and pick these objects using a gripper or a suction gripper or a grasping mechanism. The problem can be divided basically in 3 steps. So first is the detection problem, where we want to detect the object, how to pick it up, or where to pick it up from. So we could either come up with the 3D pose of the object, we could either detect what kind of object it is, or we could figure out what is the best way to interact with this object. Once we have detected, next obvious step is the picking and finally placing. So picking and placing both can get complicated if not handled properly. And placing again, so we would like to place these objects in a, instead of just throwing them out, we would like to figure out what is the best place to keep these objects in the bin or the required destination. So bin picking got a lot of media coverage during 2014 to 17, where Amazon organized this challenge, the picking challenge, where it was trying to solve the problem of picking from shells. So Amazon uses these shells to store these objects. So they usually store the objects together. But if you can see, the highest points was picking an object from multi-item shell. So 20 points were given if you could basically pick up an object from the multi-item shell. And there were negative points if you are putting it at the wrong place, or you're picking up the wrong object, or you're damaging the item, or you're dropping it from some height. So placing and picking, if not done properly, were giving a negative point. So the task was for the robot hardware and software to attempt the general task of picking and placing these items on shelf. So this challenge actually moved this field forward. There were a lot of research papers published during this time by leading universities all over the world. So the problem seems easy. For a human, it's fairly easy picking up objects from a bin. So why is it still a challenge? So objects will come in all shape sizes, basically different colors, orientations. So you have to figure out where to pick them from and what is an object, uh, segregating different objects, detecting, okay, these are two different objects. It could be different shapes. As you see, there's a lace packet. There are some cream packets, circular cream objects. And there's, I think this is some sort of Maggie packet. And finally, the most challenging is clutter. If you look at this bin, most of your classical methods would not be able to detect where one object ends and the other begins, because there's a very close, so the color is not enough information for us to figure out, okay, this is one object, or the depth. You will see a lot of times depth will also be, basically there'll be no separation between one object and another object. So that is why this problem can get very challenging, especially if you look cluttered scenes. So I'll talk about how we approach this problem. Um, so our system description, basically we have an overhead sensor. We have a cobot, which is helping us in picking and placing. Aim is to pick and place these objects using the sensor. These are randomly placed objects in any shape, size. The challenges, as I talked about it, is the clutter and the uncertainty of the environment. We don't know what kind of objects. We may or may not have that information. It depends on how this warehouse is keeping its inventory. Some of them actually keep a very good inventory where they have the 3D model of the object. Some people don't even have images or the L length, breadth, height of the object they're storing. So we want to create a solution where if we have this information, we'll use it. But if we don't, we have a generalized solution which can understand what an object is and pick it up. So few steps which are required for this to happen. First step is obviously camera calibration. We would need camera properties like the focal length, CXCY. I won't go into the details, but this is a solved problem. This is not a challenge. Another important step is figuring out how the camera and the robots in this 3D space, how they're located with respect to each other. So we have an automated algorithm for this. So we have basically sampled certain number of points spread in a 3D space where we have an attachment uh, which helps us to locate this marker in 3D space, and we detect this marker in image also. So we try to calibrate the tool of the robot with respect to the camera. This is required because when we are detecting an object in camera frame, we have to convert it into robot frame of reference and give it to the robot. Another few utilities is bin detection and tracking. So we could have a stationary bin, we could have a moving bin. It could be on a conveyor. So it is important to detect this bin. Also, it helps us to basically set up some high-level logics, pick from one bin one, place it to bin two, and things like that. So these small tools help us to create smarter logics of picking and placing. Bin detection also helps us to focus on the region of interest instead of basically looking at the area around the bin, which is of no interest to us. We can focus on the bin. So we simplified the problem for us in the initial phase. Sorry, sir. Sorry.
Yes,
Yeah.
go ahead.
Yeah. So we tried to simplify the problem. Let's say we said let's start with.
No, sorry, Chetan has a raised hand. I don't know whether you want to ask some question. Udahan, please.
I actually had a question, so that's why I don't know whether it's appropriate to ask a question.
Sure. Please go ahead.
Yeah. So
Yes, sir. Please go ahead.
Yeah, I mean, from the videos, it looks like that the camera is stationary and perhaps somewhere on the top of the bin.
Right.
Are there any versions of the problem where the camera is also on the moving arm or something? Because the motion of the arm can give us different perspective of the object, and which will indirectly help in pose estimation.
Definitely, a multi-view detection algorithm could help us solve the problem of shadows.
Right. So having a camera on the arm can actually.
Yeah. So we did that setup. We did try it, and in the end, the algorithm more or less remains same. So we tried when we moved the camera to a different angle, it still worked. But we initially wanted to solve a stationary problem, so we did not really turn that into a product. But there's a parallel research going on in that direction also. So figuring out, so me being from software, I try to avoid as so I usually avoid getting too much into mechanical setups. So there was no 3D attachment available to me at that time. So later on, we did come up with a 3D attachment. The problem could be solved with 2D also. So we did try that out, but I would not be covering that in during this phase. So MIT also did try to solve it using multi-view and sending that output to the deep learning. But yes, that is a very valid approach to solve this problem.
Yeah, so one multi-view is that I have two cameras in a stereo setup or similar setup, but the other is I have a single, I mean monocular but moving camera. So that also multiple views.
Right. So that is one of the final. I'll cover it at the end of the.
Thanks.
PPT. I'll go over it.
Okay.
Yeah. So as I was saying, we started with picking up boxes. Boxes are easy. They're planar. Their shape is easy to identify. So we took a lot of assumptions to basically reduce the complexity of the problem. Our aim was to use low-cost sensors because there are 3D sensors which go up to 6-7 lakhs. But our aim was to can we come up with regular RGBD sensors, something what Intel offers us or Kinect offers us, or a stereo camera. Uh, we relied heavily on point cloud processing and image processing techniques. Uh, so we did publish something in Agra. This is the Australian conference. So I'll go over the. So what we try to do is basically we figured out the edges, and basically we took the gradients, we tried to complete it and create a mask of the object. We use that mask. We segmented out the 3D points. We tried difference of normals to further improve the edges, separate out two objects, and then we did a plane estimation. And finally, using this plane estimation, we were able to detect the pose of the object. So fairly simple algorithm. It worked decently well for uh, boxes in the clutter. So if you see the video on just above that, it was working using this camera. But quickly we started facing issues when basically a similar color object or white objects are placed next to each other. The gradients will go missing, and the difference of normal will also not give us that separation. So we had to basically figure out how to improve this initial masking node to finally feed it back to the algorithm, which could again give us the picking. So what we did was we tried different neural networks, and we found something which did better than simple gradient, simple edge extraction. So if you see the output of the bin, if you see it has, there is no lays in most of the other gradient. If you look at the circular object, it is a complete circle. So this network was giving us output, and we tuned the network to basically focus on the outer edges rather than the whole every gradient in the image. So this gave us a very good sense of object boundaries, and we could use this again inside the previous algorithm and continue our output. So here, if you see, we could place a couple of white boxes next to each other. So when the boxes are not in a very ordered fashion, it's an easier problem than when they're perfectly stacked together. That usually becomes more difficult for us to find these edges or depth gradients. So we were able to improve this algorithm, and boxes was something we became very confident on. There's boxes we can do. Further, we can improve this algorithm if we have any sort of product information. Uh, for example, if I have the length, width, height of the object, that can go at the later stages of the algorithm for further filtering. If I have an image, then that image can further improve the output of the previous algorithm. So that is why what we try to do is fuse multiple outputs from different algorithms and finally have the final intelligence at the last layer. Uh, calling it a layer, but it's finally our algorithm is trying to make sense of all this information, and we can add or remove this data when and if it is available. So moving forward, now we wanted to, moment we did this, our senior management came and say, why not cylinders, why not triangles, why not different shapes, why not chips package? And yes, that's, we don't only have boxes in the outside world, we have all sort of objects. So can we extend the picking capabilities to any shape or size? Can we come up with a generalized detection pipeline? So yes, we were able to do that. If you can see from the video, we are able to pick up now any object. This is just a view of the UI. So so when we went back to figure out what will be the best way to do this, we found something very interesting. So FuseNet was doing something similar. It was a semantic segmentation network, which was using depth and RGB encoders. And basically, it was doing fusion at every step, so that depth information at every level is getting fused into the RGB encoders. And there's a decoder network, which basically gives us the segmentation. So it is a typical encoder-decoder architecture, but they added this depth head, another head to the network to add in extra information. So this is basically something of late fusion of depth. So some people have added depth to the first layer itself, but this usually, because they are in completely different spaces, this usually gives us a better output. But the problem again, we ran into the same problem where when we stacked objects together, the boundaries were overflowing. So what we figured out is, can we use, why not add the edges, which were working very well for us, as another head? And why not use approximation of difference of normal algorithm, a faster algorithm? And can I add these multiple layers? So instead of relying hopefully that the RGB encoder will pick up these edges, I basically try to force the network to use these outputs to give me a better sense of object boundary. So yeah, so as you can see, this is one of the outputs. So what it gives us is the area where I should pick this object from. So as you can see, so we get the segmentations, we do a couple of other filtering over using the depth, and finally we are able to generate the points. How to pick this? The picking order can be decided by the logic layer above this algorithm. So we have a deep learning model for detection of these pick points. It works on any semi-opaque object. We are focusing on the task of picking. We are focusing on pick points rather than object boundaries or object detection, because that is what we finally want to do. We want to pick these objects. And so few other mentions here, squeeze and excitation layers is what we added to this network, the FuseNet. So that we found it very interesting. What it does is basically scales the convolutions. So it gives network the freedom to figure out which feature map has more information, which is useful for the current task. So it does a weighting of the feature layers. So these were added at multiple steps on the network. And we use fire modules to reduce the number of hyper parameters. So I've put them into the reference. These are both are interesting reads. So we had a new architecture which was actually doing what we wanted to. Uh, Now it was able to solve the problem of detecting any object, picking up basically any object. So I'll just go read it. So this is the reason I'm showing you this case is the bin is blue, the shirts are blue. So this is a fairly complicated problem for the network to figure out. The boundaries, the shirts are pretty thin, so the boundaries are almost close to each other. So the network here has figured out where to pick these objects from. And also it has generalized pretty well on different kind of objects. So it can not only pick up shirts, it can pick up different objects. So we were able to achieve about 11 picks, and this was because of the limitation of the speed of the robot. We can go further up if we optimize the path of the robot, where to drop, where to pick. So it was able to empty the bin. The bin contained a lot of different kind of objects. And this kind of architecture. So this is also not an end-to-end architecture. We basically take the output of the network, and again, we have certain final post-processing steps which we use to further make it a robust detection. So, so the few learnings which we found during this task, we started with data labeling, and we figured out, okay, this So I would have to basically either assign one person to do this all the time. So instead of that, we started using a lot of simulated data, basically 3D models and creating these bins. So Amazon, AWS, and NVIDIA have given us few tools to do this, where you can manipulate the scene. Uh, the tools can be written by us also, but they have already given something to solve the exact same problem. Uh, Augmenting the real data, adding more noise, playing around in the luminous field of the images can help us to improve the network performance in case of lighting change, or even making it robust for when I switch the sensor from one sensor to another. Self-supervised network methods was something we were playing around with. This can help us get rid of the dataset problem. If I can basically figure out a way to generate dataset I'm training the dataset. So basically, I don't have to label the data. This can solve my labeling problem, and the hard work can be done by the algorithm itself. Uh, Another step we did was generate data as you test. So once we have trained model onto for certain epochs, we were able to pick up objects. So we used while we were testing this, we were picking up objects. We used this data. Every time the object was picked up, we used to take a snap of the bin. We knew what was picked, so we used other intensive methods to figure out what is the right pick point to detect to pick up this object, and we added to the data set. Uh, End-to-end networks is something when we tried for end-to-end solution, they were giving us good results. The problem was when it failed, we were left with very few steps we could do to actually fix that problem. One step was hopefully give it more data and hopefully it will learn this, or we are basically in a fix. We have to either retrain. So what we like to do is basically have multiple networks, one network giving input to another network. So I can train these individual networks and I can basically debug where the error originated from. Um, Also, as I talked about squeeze and excitation and fire modules. So the configurations which was available in the paper was not the best configuration for us. So we basically played around a lot with where to put these fire modules, where is the right place to place the squeeze and excitation layers. If possible, which we try to do is automate this, basically have a algorithm which is generating different configurations of the network, and it is automatically training overnight or over the weekends or days. And eventually you could figure out, okay, this network is the best, instead of we manually sitting and figuring out which is the best configuration. Um, Simple of classifiers can help us improve robustness of the algorithm. As we saw earlier, having one algorithm can result in basically errors. So having different classifiers, basically having some sense of object from edges, using classical methods and using the deep learning methods to figure out what is the best pick point is usually more robust, where even if one of the algorithm is giving you a wrong output, the others can help you to basically reject that information. Uh, I'll briefly talk about software architecture. So bin picking, we talked about algorithm a lot, but in the end, bin picking is a system. Uh, it has to be deployed. It has to be uh, changed over time. There'll be over-the-air updates, and we don't really know what is the best method going forward. So it makes sense to basically separate out your components into different modules. So basically, a robot should not be basically interacting with the vision system at all. It makes sense because we don't know which robot we would be using. It would depend on the problem. It could be a spider robot. It could be UR5. It could be any robot. So the implementation of robot, we want to separate out from vision. Also, we would like to have a wrapper around every class. so that when my vision is interacting with the robot, it is talking to this outer layer. So when the robot changes, no other logic, no other component has to change. Same goes for vision. So we fix the interfaces for vision, and we basically swap out from different algorithms. The output is already fixed. This kind of output is what is expected. And my logic layer or user interface or the robot class need not be affected. Another question we had to answer was where to tightly couple the system and where to keep it modular. Vision algorithms are intensive. So more modularity you do, there is more data copy, and you will lose out precious time in copying of data instead of actually doing the inference or running the algorithm. So we try to keep the vision algorithms slightly tightly coupled, the depth and normal estimation algorithms closer to each other. But robot and vision and other algorithms will be kept modular. So it helps us to have certain adaptability also. Plug and play architecture for rapid prototyping and testing. If I come up with a new vision algorithm, I need not write too much of it. I just plug in the network and my system is already ready to be tested. So multiple people can be developing new architectures or new systems. If I have a new robot, somebody has written the class of the robot and it can be quickly tested. So that can be very useful. And it makes sense to have a separate outer layer, which basically takes care of flow of data or the logic. For example, if I have to detect a bin and then detect and pick up an object from it. So those kind of logic should be at a higher level, which could be basically eventually be modified by the user itself. The user interface could actually play around with uh, the logic of the whole operation, because we don't know what the site requires or what the final user requires. So this helps us give certain adaptability to the system and certain powers to the user. So we tried this algorithm. We integrated with Omron, UR5, ABB, Kasov, and a lot of other robots. This usually is this can be implemented in a day, if not less. That is because we have kept everything modular. So plugging in a new robot, just figuring out how the robot interacts, and just writing one file of code to actually integrate that robot with the system. Um, we like to work with cobots because we are working in a shared space with the humans. Uh, Traditional manipulators, we would have to set up safety cages around the robot. Now, because we're working with cobot, we could also think of interesting ways where humans and robots can actually do picking from the same bin. Coming to way forward, a generalized detection module where we want to head is a generalized detection module which has an understanding of what an object is. So detection, when I go to detect different kind of objects, there'll always be a limitation because uh, for a giant like Amazon, they have hundreds and thousands of items to be picked. So no network can actually scale up to so many items. So I cannot do a detection of each and every object. If picking is the task, detection really does not add any value. Uh, can we learn from our mistakes? Uh, if at site the robot was not able to pick up the object, what will be the best way to use this information? Because we have the stored information, what will be the best way to use this information to improve the learning of the robot? So next time it can actually pick up that object. Uh, so what we want to go towards is lifelong learning, where the small nudges from the user can help the robot to pick up new objects or learn about new objects. Cloud deployments. This could help us reduce the cost, basically not having a GPU at the edge rather than having a powerful GPU at the cloud, and using 5G, sending out images to that cloud and getting the data back. Photorealistic simulation of the environment can be very helpful. It could uh, reduce the need for real data annotation. We want to make our network more robust to noisy data. Sunlight, different lighting conditions shadows can lead to a lot of noise in the data. So how can what will be the tricks to figure out the best way to deal with this problem? Transparent or translucent objects, for example, glass bottles, bulbs, for example, even fragile objects. What is the best way to deal with them or train for them? Because the camera cannot see them. So no light-based sensor can actually see a fragile object, a translucent object. So there are methods to do them, but they basically end up overfitting for these objects and they lose generalization while doing that. So another approach is we figure out what kind of object it is and we switch between networks. We switch from one network to another once we know what kind of object is coming to us, but that may or may not be possible at all times. Great. Thank you. And any questions?
Thank you, Sarthak, for a really interesting talk related to computer vision. So let's take up the questions now. We already have 2 questions in the chat box from Professor Chetan. You can take them up.
Just a second.
Yeah, and others can now unmute themselves and raise their hand before that.
So if we restrict ourselves to picking boxes, could we have placed QR code in it? And definitely QR code is one of the easiest way to do it. So what we can do, we can get some information, but we cannot usually alter the established processes. For example, if I want to pitch my product to Amazon or IKEA, I cannot really ask them to add anything onto the product because adding a small step in their cycle will take months, if not a year, to actually add that process. And so when we are designing our own warehouse, yes, we can do a lot of these tricks to improve the adding a QR and making this problem easier. But for an established warehouse, this might not be possible. So we did try a lot of, so another question from Chetan is, can we estimate 3D bonding boxes? Could this have been used? I'll just go through the paper. So we did try a lot of 3D bonding box based approaches. Problem was when in a lot of clutter and unknown objects, we saw the bonding boxes going combining 2 objects or multiple objects, but obviously it can be trained better. But what I wanted, so Facebook has, I think, recently published something where they are trying to generalize the understanding of what is an object. What they're trying to do is, given a scene, it will try to tell you these are the objects. So it is an object understanding rather than, it's not teaching on what kind of object it is, but what is an object. So I was not very happy with the results, and we could have done without 3D box estimation, but 3D is a problem we are parallelly solving because in automotive, automotive or manufacturing, we already know the shape of the object. We would have CAD models, and we could use these CAD models to actually detect the accurate 3D shape. So that will be a different problem, handling that problem.
See, normally, even in the case of, let us say, unknown objects,
right.
So one, there is an open set object detection,
right.
where you can actually handle the unknown objects also. But on the other hand, even if, let us say, you have new objects, most often the bounding boxes are still correct. I mean, you are not able to classify which object this is, but the box still comes out to be okay. So for example, so what I'm expecting, that if you have, let's say, 10 different kinds of boxes, at the box detection level, things may still be working okay. You may not be able to say that this is object A versus this is object B, but The box usually comes out okay.
Right. So this is what we saw with other objects also. So when we are adding new box, we can do different shapes. Basically, it can try to cluster different kind of shapes.
All correct.
Yeah. For example, even for 2D detectors like Detectron or YOLO, adding a new similar shape, it could quickly, pick it up also and give you. I'll have to go through this paper what exactly it does. So few of the state of the art things which we tried, I could share this privately with you, were on clutter. On I think the first image I tried to show you. This is where it was. And also, as I told you initially, the depth is not something. So, for example, this image. So, depth is using a stereo camera. So, a lot of reflective surfaces would have large black spots, and there'll be a lot of shadows in the scene. But it'll be interesting. I'll just after the uh, after the meeting, I will go through this paper and I'll quickly try it out on a data set whether this could work. But initially, for me, the 3D box detection did not, 3D bonding box detection did not really scale up very
Okay, thank you.
well. Right. How humans,
Sarthak, sorry to interrupt, but someone has raised his hand. He's waiting, I guess. So, Sri Krishna,
right.
go ahead.
Sir, you talked about what you call as two or more, one neural network-based method and another classical method. And
Right.
what is the classical method you use, and how do you handle the trust in one something like multiple sensor? Will it be handled like multiple sensor inputs and you plug it in to a Gaussian, and you like use both the data to make the Gaussian function like higher and more narrow or something like that? How do you handle
Right.
the trust between the two?
Right. We could go into those classical methods where we could figure out how to weigh. We could learn these weights also over time. But most of the times, the engineering solutions, lot of lot of checks and lot of basically simple weighted averaging also helps us. So, for example, I talked about having different information regarding the product. So, for a lot of large warehouses, we get LBH information. So we use this information after the network to further prune uh, our information. So we also initially there is a calibration step where we detect the bin and we have certain sense of what depths are allowed. Uh, Also, we basically check the smoothness of depth and things like that. So these are something, because I cannot force the network to do. This is something I do in the post processing step of the network output. Does that answer your question?
How do you no, if you're using as a post processing step, it is not like what I thought was that you had like those running parallelly, and you had like you suppose you had this, you're also checking with the other one and see that like seeing the trust of both and seeing whether both are satisfying certain condition and you're taking the final thing or something like that, or you're using like if suppose the accuracy in the deep learning was not very good, you'll also check up with this such so that what I understood was that you check up with this such that it is okay and you proceed with that. It is as a fail proof step after the deep learning. That is what I understood from yours. And like how do you handle the trust between how much probability will be okay like I don't know how to explain it properly, but
Right. I understand. So one thing which was very interesting was when I run the network on the same image twice, the output would obviously vary because the depth is not consistent. In image also slight variations are there. So that itself, averaging that out itself improves the output of the. So some sort of temporal fusion over this data itself improves my output over this. So there, we did try uh, CRF for this. Basically, CRF, I added an edge and the output of the network. Um, to improve this. But finally, these were more of heuristic checks over the network, and what we did was some temporal reasoning, uh, whether this place has been. So basically, I'll do a Bayesian update over these confidence scores of this object, and once I get these stronger heat maps, and then I can act over it.
So, sir, if you suppose you run those two parallelly, do you consider is there any gain in like using the data obtained by both the heuristic method and the deep learning method, the comparison between the two on the same image for another learning process? Suppose you take the data from both, you store everything, and you try to use it for making another network which is better when you take in both the inputs. Something like that. Output of both the.
That could definitely work. So whatever I am thinking, whatever method I've written, the neural network could estimate a better function for it, definitely. But as I do that, as I keep on increasing the depth of my network, deployments is something I also have to parallelly consider. So there's a limit to, so with adding more heads to the initial FuseNet and adding a few more, that itself made the network pretty slow. So for example, if you see the runtimes, these are not very good runtimes. And this 4 GB is also something of a overkill for me. I would like to, eventually what I would like is to run this algorithm in something like a nano. So if I could do it under a lakh, so adding more networks will obviously, given more data, obviously that will improve the output. But that is also something I always consider, that wherever I could avoid a network, I should, because there will be a hardware cost eventually.
So hardware limited right now, like the limitation is hardware. So this could be broken with like sending the data over the like internet and processing somewhere else. Like
Yeah.
like leverage large server.
True. So cloud deployments is something we are parallelly. So we are testing out certain implementations with Intel, with 5G. So we want to figure out if 5G within a warehouse, if we can, quickly, what will be the latencies, whether these are reasonable. Then we could actually have something, we could go for multiple inferences of the same image or different, and do a better fusion of it.
Yes, sir. Thank you, sir. Thank you.
Thank you.
Okay. So we have two more questions, Sarthak.
Right. Yes.
In the
So
chat
how
box.
is how the
Yeah.
human is sensed by a robot? What sensor is used and how it is implemented so that it's a work environment for easy access. So cobots in general are collaborative robots. They come up. They already have torque sensors, and at every step they are computing the torque required. So they have hard limits. So to adhere to the standards, they have to, moment a human touches them, they will go into a safety stop. So one way is to design the workplace such that they are not intersecting continuously, the human and the robot. But even if the human comes in front of the robot will not hurt the human, because it has these. So torque sensors are pretty expensive, and most of the cobots do that. If you could actually see how cobots behave near a robot, near a human, you will have some understanding of the certain emergency brake which is applied in the cobot. Once that brake is applied, it can, after a certain while, continue working, continue doing its job. Have you explored event? Sorry, does that answer the question, Mahesh?
Yeah, thank you, sir.
Thank you. Have you explored event cameras for this purpose? Do you have event cameras? Is something I've wanted to try for even my mobile robots. And so event-based camera, I'm not pretty sure how it will help here, but for mobile robots, they could have helped, definitely, could have done some smart things. But as I talked about earlier, they are right now not very cost effective. And India being a cost sensitive market, adding a sensor, these are certain considerations I have to think about before I can choose a sensor. So there are a couple of good sensors from SICK which give me a very precise depth. but the cost is almost 10x the sensors I'm using. So that is why I go for less precise sensors, and hopefully my algorithms can work with these sensors, and my system can still perform. Right.
Yeah, Sarthak, so you can take up the last question, and I will add that it would be fine, I guess, that if someone is contacting you after the talk for the questions, you can put up your email.
Sure. Sorry, can you repeat that?
Yeah. Yeah, I just wanted to ensure that if someone else is having further questions, they can email you, right?
Definitely. Sure,
Yeah, so you
please
can
do.
put up the email in the chat box because we are running out of time. Yeah, you can take up the last question. Yes.
So I would love that, and I would love to basically have this discussion I was having with Dr. Chetan Arora regarding what could be the other possible ways where I could further improve uh, the reasoning, the object reasoning of my networking architecture.
Sure.
Thank you. So if QR is used, then objects will have to be placed such that QR code is visible to the right. We will have to take care of that definitely. Occlusion is something, so that is why QR was something Dr. Jitan Arora had suggested. And so again, there could be, so as I talked about separating out the logic layer. So in the logic, you could, once you see any object, if none of the QRs are visible, that is the worst case, but you could, um, if you're placing QRs, you could place it on all four sides and things like that. But yeah, QR based solutions can get very complicated. So QRs, there is a wear and tear and things like that. So that is why I'm not fond of that solution. We would like to go towards a more human way of picking up objects, because we don't really need these kind of things. We just can pick up any object from any clutter. So that is where we want to head, basically having a reasoning of what an object is, how to pick it up, rather than detecting something, some specific features. Great. I think the questions are done.
Yeah. Thank you, Sarthak, for a really amazing talk and for answering the questions of our audience. So I would now like to thank you from the side of IHFC team for giving a really intriguing talk. And I would now like to ask our director, IHFC, Professor Saha, to felicitate our speaker and say a few words. With Saurabh, you can share the screen. Yeah.
Yeah, so thank you, Sarthak, for the nice presentation. And I wish you, all the best. And it has generated a lot of enthusiasm and the interest. That's, I was hearing the argument or the discussion with Chetan also, and then the Mahesh and others. And hope our enthusiasm continues. So we look forward for the next month's speaker, again from Edinburgh. And this is a small token of appreciation from Springer, 150 euro gift check, rather e-voucher actually, for a book to be handed over to. Thank you. All the best.
Thank you, sir. It was an honor to be here.
Thank you, Sarthak. And we'll again like to thank Springer for showing their support with IHFC. Thank you everyone for joining in the talk. We'll see you again in the next CoboTalks and the coming CoboTalks also.
Yeah.
Thank you.
Bye-bye.
Bye-bye.
Bye-bye.